share my screen. So hello everyone and welcome to our start of our review for Math 211 2020. What just happened? 2021 December. We're ending 2021 and we are going to start reviewing now from the very beginning. 3 days of review: Thursday, Tuesday, Thursday. And we're starting with chapter 1. So chapter 1, of course, I'm not teaching this again. So this is going to be a quick run through of each section, just ideas as opposed to examples. But chapter 1 dealt, and you can just like make a bullet list of things to know. The things that I point out is, oh yeah, this is important. Things that I stress, so you'll know, oh, he stressed that. Maybe he thinks that's important enough to ask about. So we have empirical and theoretical probability. This is where we started the year, started the semester. Empirical and theoretical probability is the difference between experiment-based likelihoods versus theoretical likelihoods. If I flip a coin and I say, what's the likelihood of getting a heads? You say, oh, 50%. That's theoretical because you didn't do any experiments to get that. That's just logic. That's just the way life is. But what if I whittled my own coin and we're not sure if it's fair or not? You can't say 50%. The only way of truly knowing whether or not it's fair is by flipping it a bunch of times and taking your empirical data and using that as your value. So here we had a bent nickel case, right? Bent nickel, is that 50-50? I don't know. We took some data. Remember these? We did this in the beginning of the semester. The graph goes up, the graph goes down. I was a homework question on it. I even had a quiz question on it, if you recall. So this was something that I really stressed. Of course, the law of large numbers. I keep saying that one big word. It had 5 syllables. Anyone recall that 5-syllable word that we use when we're dealing with the law of large numbers? I'll give you a hint. It starts with the letter S and it rhymes with minimization. No, nothing. Stabilization, that's it. It's been so long, yes, but it's all about stabilization. That's right. I thought maybe my clue might have been too much of a giveaway, so it looked like it wasn't. That's good. All right, but the law of large numbers says that you keep flipping and flipping and flipping and flipping and flipping until you reach a stabilization. That's when you know that you're honing in on the true value. That's the law of large numbers. You always hone in on the true value if the sample size is big enough. Okay, then we had some rules about probability, rules about likelihoods. For example, all probabilities must be between 0 and 1. More than 1 means it's more than certain. I mean, how can you be more than certain? It just doesn't make any sense. Less than 0 means it's less than impossible. What? That doesn't make any sense. So they're all between 0 and 1. 0 means can happen. 1 means it will happen. And in the scenario when they are equally likely, we even have a formula. The formula, the number of ways it can happen, divided by the total number of outcomes. This is the probability of an event, A. And of course, we all have the fact that we also have the last part, which is the likelihood that an event does not happen is 1 minus the probability that it does happen, because those two things have to add to 1. It's just merely a rearrangement of that. So these are, I believe, everything in chapter 1. Also the sample space. When you do an experiment in probability, we don't know the outcome in advance. You flip a coin, what's it going to be? Don't know. You have a child, what's it going to be? Don't know. You roll the die, what's it going to be? Don't know. You don't know what it's going to be, but you know what it might be. You know all the possible outcomes. The sample space is a collection of all possible outcomes. And it's got to be one of them, but we're not sure which one. That is the definition of a sample space. So if you look at the sample space and you look at all the possible outcomes, we can then list them all. In this case, flipping, it looks like 2 coins. It could be 0 heads or 1 head or 2 heads in total. And we can write the corresponding probability next to it. And if I add up all those probabilities, what must it add to be a valid probability distribution?
100%.
Got to be 100%. Okay, all the likelihoods added together must equal 100%. Okay, none of them can be negative. That doesn't make any sense. So if you have that, you have a valid probability distribution. And we did some more examples and some more examples and some more examples, and then we had the homework. So that was chapter 1. So if you look at chapter 1, recap, what do you need to know? The difference between empirical and theoretical probability, the basic rules of probability, the idea of a sample space, the law of large numbers. Did I miss anything in my recap of my recap? Or is that it? I don't know if there's anything I just missed in my recap of my recap. I think that was it. Any questions on chapter 1 and what specifically what you need to know from chapter 1? All right, now let's then move on to chapter 2. Chapter 2, I'll share my screen again. Okay, chapter 2 was on simulation. We didn't do much simulation throughout the semester, but we did at the end, if you recall, all those sampling distributions where we simulated by getting sample size, and we had these bell curves. We did a lot of simulation at the end. But chapter 2 on simulation is hold on, can you guys hear this? Or is that loud? Do you guys hear this stuff going on?
Mumbling, yeah, a little bit.
Okay, hold on 1 second. I'm just gonna get them turned down. Okay. Apparently, I don't know any Spanish. Okay, so simulation. So what is simulation? Simulation is when you don't do an actual experiment. You do a different experiment instead. Perhaps it's less time. Perhaps it's less resources. Or just easier in some way to do a simulation instead. So if I say, hey, let's flip a coin, and you say, oh, I don't have any coins. Oh, no, we can't flip a coin. Well, flip something else. That's 50-50. It doesn't have to be a coin. You're simulating a coin with something else. So the idea of a simulation is when you do a different experiment instead. But the probabilities have to match. Okay, if I simulate a 50-50 situation, I have to do something that's a 50-50 situation. I can't simulate a 50-50 with an 80-20. It doesn't make any sense. So everything that I simulate with has to match likelihoods. I can use spinners, I can use dice, I can use cards, I can use coins, and I can use a random number generator. So we had a bunch of situations like that, of simulations. And what are the steps in a simulation, sorry. First, you have to describe what you're going to use can model the actual scenario. So for example, I know that in my school, there are 70% boys and 30% girls. And I want to pick 10 people at random. How many boys and girls do I think I'm going to get? Well, I don't want to actually pick people because they're all in their classes and they're all working and whatnot. So instead, I'll just take 10 objects, label the first 7 as boys and the last 3 as girls, shuffle them, take one, shuffle them, take one, shuffle them, take one, and so on. I am describing how I'm going to get my outcomes with my simulation material. It's just a word description of what you're going to do. And then you just do it a bunch of times and you say, this is what I got. Hey, I did it and I got 8 boys, 2 girls. And hey, that's likely, that's not likely, analyze the situation. Do it lots of times. You can use random digits. We did that. With the random digits, if I use 1 digit at a time, it's got to be 10% each. If I use 2 digits at a time, it's got to be 100%. If I do 3 digits at a time, it's 1,000, not 100%, but let me rephrase that. If it's 1 digit at a time, that means there's 10 possible outcomes. Each digit is one of those 10. 2 digits is 100 possible outcomes. 3 digits, 1,000 possible outcomes. What if I only have 998 possible outcomes? What do I do then? Well, I can modify it by saying, okay, only 998 outcomes, fine. We'll do 3 digits at a time, but 999 and 998, the last 2 possibilities, if we get those, we'll just say those are do-overs, they don't count. So we remove a couple of the possibilities so that we only have 998 of them left, and then we just go down the line. So we did examples like that, and what's this? Why isn't that? Oh, there we go. And how many runs should you do? So look at this number here, by the way. This is all the way back in chapter 2. What was that formula that we had really all the way at the end of the semester that relates margin of error to sample size? Anyone remember that formula near the end of the semester that connected margin of error to sample size? Spoiler alert. Oh, not spoiler alert. Maybe a spoiler alert. Spoiler? I don't know. Whatever alert. It's the same. Oh, someone chatted it. Yes, n equals 1 over s square. 1 over ESQ. 1 over ESQ.
The square root of n over the 1 square root of n.
So E equals, S stands for squared. Sorry, I didn't realize that. But no, yes, it's n equals 1 over E squared. Oh, ESQ's. Oh, yeah, that makes sense. Right. So n equals 1 over E squared. So the formula all the way back in chapter 2 is the same formula that we had back in chapter 23, whatever it was.
23.
It all comes full circle. Not like a real circle. That's like a geometry thing. And this is not geometry, but you know what I'm saying. Anyways, we had that, and that's the end of chapter 2. So are there any questions on what you need to know from chapter 2?
I think there was a homework that on chapter 2 that I did wrong. I think it was with the digits generator
Well, let's take a look.
for the random digits.
Do you recall which?
And it was something with using 2 numbers instead of 1, if that makes sense.
So here's the homework. You see it, right? I'm still sharing my screen. Yeah, I am.
Yeah.
So do you remember which one it was?
I could look for it in the next class or whenever.
Yeah, we could take a minute or two. I have a question. Can I take all my notes or just one sheet? Your whole notes, take a notebook, take a pile, bring it all. Of course, just be aware that the more you have, the more that you're going to be doing this, looking for things instead of this, writing things. The more you know and the less you have to rely upon, the faster you're going to be able to answer questions, right? So the more you don't know and the more you need, you know what I'm saying. So, but yeah, bring everything you want, not anything you can carry in with you, but you can bring all the notes that you would like to use. All right, so rules of counting. Chapter 3, rules of counting. So we start with the fundamental principle of counting. It's fundamental. Basically, if Pat has 4 shirts and 3 pants, how many different ways can Pat pick a shirt and pair of pants? The answer is 4 times 3, 12. The principle of counting is if you have a certain number of ways of doing one thing, and a certain number of ways of doing the second thing, and a certain number of ways of doing the third thing, and the fourth, and the fifth, and the sixth, and so on, in succession, and you want to know the total number of ways of doing them all, you just multiply them. And we had the area model to demonstrate this. We see 4 by 3, there's 12 boxes. We had a tree diagram model, first choice 4 choices, third, second choice 3 choices, and you add up 12 at the end. different ways of modeling it graphically, but at the end of the day, you just multiply. That is the fundamental principle of counting. We also had permutations. Permutations is when you are, you want to know the number of ways of choosing a certain number of objects from a larger collection of objects. With what condition? What condition is necessary for it to be a permutation, as opposed to that other thing, which we'll list in just a few seconds. Yes, Tyler, the order matters for a permutation. And if the order does not matter for a permutation, it's called a combination. And you should certainly know the formula for permutations. And you should certainly know the formula for combinations when the order does matter. And that's homework number 3. That's it. So chapter 3 was really, really quick. We had 3 things: the fundamental principle of counting, the idea of permutations, the idea of combinations. Questions on chapter 3? Oh, yeah. Okay, no questions on chapter 3. Let's move on to chapter 4. Chapter 4 was the addition rule. Now, the addition rule is our first way of adding events together to combine them into more complicated events. And it starts with the words and or in mathematics. Of course, the word and is straightforward. This and that, you want both of them to happen. I want you to pick someone in the class that is both female and under 5'3". Well, whoever you're going to pick has to be female and under 5'3". Both conditions must be satisfied, or else that person is out. So all the males are out, and all the taller than 5'3" females are out. And it's got to be both. Okay, one of the two. Is that good enough? No, it's not. I want both. That's and. The word or is a little more complicated because in English, the word or has 2 different meanings. Sometimes when you say or, it's one or the other to the exclusion of both. I flip a coin. Was it heads or tails? Well, it's not both. I'll tell you that much. It's heads or it's tails, but it's not both. But if you go out to the restaurant and they say, do you want, do you want orange Fanta or Sprites? And you say, yes, please. It's totally okay to have both because they're both great drinks, right? 2 of the best ones out there. Nothing beats A&W root beer, of course, but still orange Fanta and Sprite are still high up on the list of amazing drinks. I'm sure we all agree on this. Nobody's arguing, so we'll just go forward. So this is the addition rule. So when you have mutually exclusive events, also called the, someone texted, if she's arguing or he's arguing, I'd be very upset. Cactus cooler? Cactus cooler. I don't even know what that means. Is that a beer? It sounds like a beer. Is that a beer? You guys are too young to be drinking beer. You're all under 21, right? You guys can't have alcohol. Cactus cooler. It's
Wait,
a
what are you serious? You don't know what a cactus cooler is?
Apparently not. Okay. Are you cactus cooling shaming me? Is that what you're doing? Are you cactus cooling shaming me?
I'm just so surprised.
Totally inappropriate. Okay. This is
You
2021.
want to
Okay?
try it now since you like the orange like popsicles so much and the orange maybe you'll
Orange
like this drink.
creamsicles. Creamsicles.
Creamsicles, I'm sorry, but you just try it. It's good.
You know, my test I had last night on campus, someone actually brought 2 boxes of orange creamsicles. Can you believe that? He actually bought 2 boxes. I'm good, but I couldn't finish 2 boxes. I had 8 of them, but I couldn't quite finish 24. That's just like, that's just like even beyond my capability. All right, cactus cooler. I will add it to the list of things that I will try. But to beat A&W root
We'll
beer,
bring it to you on the day of the final. We'll
You
bring
bet.
you
all right. So, anyways, cactus cooler in quite a few gas stations. Okay, I'll give it a shot. And before I start my diet, which will be never. Okay, so mutually exclusive events that cannot happen at the same time. So if I say, what is the probability of this or that, and they can't happen at the same time, it's easy. You just add them together. There's no overlap, so I don't have to worry about double counting. But if they are not mutually exclusive, then I have to remove the double count. And we had some Venn diagram scenarios to illustrate this. It was very important. We did all these things here, very important stuff. So what's the addition rule for mutually exclusive events? You just add up their individual probabilities. This is a big one right here. What about they're not disjoint? Oh no, they're not disjoint. Well, in that case, it's the same rule except one addition. You remove their overlap. So the first one, the second one, but you take away the stuff that you counted twice, which is the overlap A and B. This was the addition rule, and that takes us to the end of chapter 4. So 4 chapters down, and you wanted me not to even ask on this stuff. This is the easy stuff there is, right? Chapter.
For you, yeah.
Oh yeah, there is that. What can I say? What can I say? All right, chapter 5, conditional probability and independence. What happens if you are given some additional information that might influence likelihoods? If I say, what's the probability of flipping a coin and getting a heads, you say, oh, it's 50%. If I say, what's the probability of getting a heads if it's not tails? Well, now it's 100%. I mean, if it's not tails, it has to be a heads. I mean, you just gave me a little bit of information that changed everything about the problem. So conditional probability is calculating a likelihood when you have some additional information. And if you recall, we had this, the princesses and the crowns example. It's like it was yesterday. I remember all this stuff. So we did this. Now, what does it mean to be for 2 events to be independent? 2 events are independent if one has no effect on the other. What's the likelihood that it rains tomorrow, given that I roll a coin and flip a coin and get a heads? How does one affect the other? They're independent. They got nothing to do with each other. Why would one have any effect on the other one? The answer is it doesn't. They are independent, which means the probability of one given the other doesn't change because the other one occurred. So it's just equal to the probability itself. That's what independence means. Yeah. And we had a way of showing independence. Essentially, if the likelihood of A given B1 or the likelihood of A given B2 and so on were all the same, obviously, if they're all the same, then who cares if B1 occurred or if B2 occurred or if one of the other ones occurred? I don't care what occurred. The likelihood is the likelihood. So this was a little test that we had from a table, which we did in this example. You should go back over that. And that takes us to the end of chapter 5. So we are moseying right along here. And I've never moseyed before, but apparently moseying seems like a pretty cool thing to do because we are moseying right along. 6. I saw shade once, but I don't think it's the same thing. All right, chapter 6. The multiplication rule. So we've done the addition rule, and now we are moving on to the multiplication rule. If you recall, for independent events, the multiplication rule was a way of determining likelihoods of the inner cells of your table from knowledge of the marginal cells. In particular, if these are independent, who remembers? I know it's been a while. This is back to chapter 6, but who remembers how to calculate this square right here, this cell, from knowledge of the margins 0.6, 0.4, 0.1, 0.9, and 1? Anyone recall how to use those to get this one right here?
You multiply.
Multiply what?
So for example, the no crown under regular girl, you'd multiply the 0.90 and the 0.40.
Excellent. Yes, you multiply the margins, 0.9 times 0.4, that gives you 0.36. And that would be this number right here, 0.36. And similarly for all of them. Wonderful, wonderful. So That is the rule for independence. So the probability of A and B, of both of them occurring, is the probability of A, which is the column, let's say, times the probability of B, which is the row. And you do that for all four, and that gives you all of your cells. So you can determine independence by using this rule here. If you get the right number for every cell, then they are independent. We had different visual models again. In this case, it's an area model like we had before for the fundamental principle of counting. But at the end of the day, it's just a model to illustrate the multiplication rule itself. Of course, it goes beyond just two events. You can do it for three. A and B and C is just the product of A, B, and C. Of course, you can't really visualize that with an area model because that's inherently two-dimensional. You can only have two, and the third one will require the third dimension, which is kind of difficult to work with. Of course, if events are not independent, then likelihoods change as you move through the problem. So if I say I want you to pick two balls, what's the likelihood that both of them are red? Well, you pick the first one, and it's 1, 2, 3, 4, 5 out of 10. So the first one is 5 out of 10, but now the first one is gone. It's out of the picture. It's been picked. So the second one's not 5 out of 10 because you don't have 10 balls, and of those 10, 5 of them aren't red. Now there's 4 reds, there's 9 balls, so it's 4 ninths. So 5/10 times 4 ninths. You multiply that way if the events are not independent. So what's the likelihood of A and B if they're not independent? It's the likelihood of the first one, 5 out of 10 in our case, times the likelihood of the second one, given that the first one has occurred, which in our case was 4 out of 9, and you go down the line, and that takes us to the end of homework number 6. So we're going pretty quick, but these are just, in the nature of, these are the things that you should know. Okay, but in terms of actual content, we did a lot of examples to illustrate ideas. But in terms of actual content, we just ran through 6 chapters of content in, a half an hour. So in terms of studying, you see that while we covered a lot of chapters this semester, like 19 chapters, something like that, the amount of actual content in each chapter is actually not that large. So it's not as bad. Of course, you have to know them all, but and it's still a lot of material, but it's not as bad as it seems, or I hope it's not as bad as it seems. And then finally, we'll do 7 today, and we'll call it short. This was like basically the first test. We talked about expected value. Expected value is how many depends on the situation, of course, but what do you expect to get in the long run if you perform the experiment over and over and over? So for example, sorry, if for example, suppose I flip a coin 10 times and I count the number of heads. So it could be 0 heads, it could be 1 head, it could be 2, it could be 3, 4, 5, all the way through 10. If I do this over and over and over and over again, 10 coins, mark how many it was. 10 coins, mark how many it was. 10 coins, mark how many it was. I might get a table like the ones shown, where you see in all the times I did it, I got 2 once, I got 3 once, I got a few 4s, I got a bunch of 5s, some 6s, some 7s, and I got an 8. Never got 9 or 10 or 0 and 1, but these are the ones that I got. And then if I say, okay, what's the average of all of those? Then it looks like the average is probably around 5. It looks like it's fairly symmetric. So on the average, I expect, even though I didn't get 5 every time, I expect on the average to get 5. So that means, while I have no idea what I'm going to get on any specific run, if I do it 100 times, I should have a total of somewhere in the vicinity of 500, i.e. 5 per time on average. Expected values are long-term averages. In the case of a simple experiment where the likelihood of success is P, and I do it n times, how many successes do I expect to have? This was the basic formula, n times P. Number of trials times the probability of success. If you think about it, if something has a 25% chance of occurring, and I did the experiment 100 times, it seems reasonable that it will occur around 25 times. 0.25 times 125. If you flip a coin 5 times, how many heads do you expect to get? Well, 5 flips, the likelihood of a heads is 0.5, 50%. So I expect to get 2.5 heads. Of course, you can't get on any one flip 2.5, which is why students of all ages commonly say, well, it's 2 or 3. No, it's not 2 or 3, it's 2.5. I know you can't get 2.5 heads every single time. So what does that mean? It means on average, if you do this lots and lots and lots of times, on average, it'll be 2.5 per time, even though you can't get 2.5 on any individual trial. Fair price. What exactly is the fair price of an experiment? The fair price of an experiment is the price that you must pay for the expected value to be 0. So that if you calculate all of the rewards at the end of the experiments and you calculate all of the costs at the beginning of the experiments, these two numbers should be the same. If they are, then it's a fair price. And here's a formula for expected value, that if you know all of the possible outcomes and you know the probabilities of all of those possible outcomes, you multiply each outcome times its probability and add them all together, and that gives you the expected value for that particular experiment. And that takes us to the end of chapter 7. So how many questions, does anyone have a question, are there on 0.9 times 0.6? Alejandro, I just saw that text. I'm not sure why I didn't see it before. I remember what it's referring to, but I apologize for just not noticing. So are there any questions for the what we just did, these 7 sections?